This, okay. Thank you for the introduction. So my name is Bhanu Kumar, and today I'm going to be talking about some preliminary results we have in our search for transfers between Jupiter-Europa and Jupiter-Ganymede resonances. This is joint with my PhD advisor at Georgia Tech, Rafael Leave, as well as my collaborator at JPL, Dr. Rodney Anderson. So we know that mean motion resonance overlapping is important for the generation of chaos and dynamical instability. And indeed, this can be leveraged for tour design in multi-beam systems. So, for example, there has been studies previously finding heteroclinic connections between, say, Jupiter-Europa resonant orbits or Saturn-Titan ones. But then the question is, as was alluded in Professor Ross's talk this morning, how about transitioning between resonances that are resonant with different moves in a given system? So now some of the earlier work in this has been done by just patching together various restricted three-body models. But really, if you want to model this properly, you should be dealing with a restricted four-body model at the minimum. Now, we know that when you add a periodic perturbation to the planar circular restricted three-body problem, usually those unstable resonant periodic orbits, they will persist as unstable 2D tori. So the dimensionality of everything is higher, so it's more complicated to do computations here. Now, so just in this talk, we're going to start out with describing the dynamical model that we use. After that, I'll briefly summarize some of the results of earlier work on computing tori and manifolds. After that, we'll talk about the method for actually finding approximate intersections of the manifolds, and then talk about some preliminary results we have on near intersections. We're still looking for true intersections of Jupiter-Europa and Jupiter-Ganymede resonant invariant manifolds. So the model we use is called the concentric circular restricted four-body problem. In this, you assume you have three large masses, M1, M2, and M3, where M2 and M3 revolve in concentric circles around M1. And of course, you're interested in the dynamics of a fourth infinitesimally small mass, a spacecraft, under the influence of this system. And this is a Hamiltonian system, albeit with a time periodic Hamiltonian, as given here, which depends on a phase angle. In this case, it's the theta3 is the angle made. If you write this in an M1, M2 cyanotic co-rotating frame, just like in the planar circular restricted three-body problem, then these are the equations of motion, and they depend on that angle theta3, which is the angle that M3 makes with the x-axis, essentially, with using the position of M1 as the vertex of the angle. So now this just graphically represents what we're dealing with. So now the key thing here is that when you take mu3, the third mass, equal to 0, this just reduces to the M1, M2 planar circular restricted three-body problem. And indeed, the equations of motion are time periodic, as given below. Now, you can also make a coordinate transformation, as given here. R is just the rotation matrix by the angle and subscript. You can transition the coordinate frame from the M1, M2 rotating frame to the M1, M3 rotating frame. And in this case, again, in this here at mu2, M2 equals 0, then you would get the M1, M3 planar circular restricted three-body problem. When again, it's periodic with that period of time. So now, as mentioned, this model is a periodic perturbation of both M1, M2 and M1, M3 planar circular restricted three-body problems. So we expect that unstable periodic orbits, those families, should persist in some form into the perturbed model from both of those planar circular restricted three-body problems. So the persistence has to do with normal hyperbolicity, KM theory, and we expect it to be up to some perturbation strength. So now the key is that we can compute these tori. So just summarizing some stuff you might know already. If you have a 2D torus in the system, you can parameterize it as an image of a function of two angles, theta 1 and theta p, where theta p is that perturbation phase angle mentioned earlier. And in that case, if you just define f to be the stroboscopic map, which is the integrate a point by the equations of motion by the period of the perturbation, then what happens is that theta p, that perturbation phase angle, comes around by 2 pi that much time. So you can basically fix its value and ignore it from this point onwards. And this reduces the dimensionality of the tori from 2D flow tori to 1D map invariant tori and the phase space to 4D. So that's just computationally easier to deal with. So from now on, everything will be dealt with stroboscopic maps. This just graphically represents the situation. Now, quickly summarizing some of our previous work, we have the method for computing these tori, which simultaneously computes the stable and unstable directions at each point of the torus. We have the parameterization towards k of theta, where theta is in the one torus. And then we could use this quasi-Newton method that we developed in this paper for continuation from either planar circular restricted 3-body problem to the restricted 4-body model. So just this is, for example, a family of Jupiter-Europa 3, 4 periodic orbits continued into the Jupiter-Europa-Ganymede restricted 4-body model. And here is a Jupiter-Ganymede 7, 5 family continued into the same model. We do see some interesting phenomenon happening at the higher eccentricities. So now, given these tori that were just computed, we can also compute the manifolds using similar parametrization methods. It's going to be a function of an angle theta and a real parameter s along the unstable or stable direction. You can compute it using a Fourier-Taylor series with the help of automatic differentiation, jet transport, just kind of a recursive order by order method. And then finally, the Fourier-Taylor series only has a finite radius of convergence, but you can use numerical integration to extend this function w theta and s to the entire space t cross r. So we get now a representation of the manifolds as a function w of theta and s, and let's say we have two of them, right? So wu and ws for an unstable manifold of one torus and a stable manifold of another, and we want to find the intersections of them. So the equation to solve is just given up there for theta u su and theta s and s sub s. So in order to find a true intersection, there's basically 3 steps we've come up with. The first is to restrict yourself to certain subsets, which you can do. And then the second is to discretize the search using as a mesh search and basically use GPUs, which are a piece of computing, certain type of computer processor to help find intersections of these meshes. And then finally, use the parameterizations to help refine the intersection to the approximate mesh intersections to a true manifold intersection. And where we are right now is that we've found approximate solutions, but sometimes these approximate solutions may not actually correspond to a true solution, but they can still be useful in terms of just being near intersections, which could lead to propellant-based transfers. So this first step is, of course, the restriction, in that you we define these sets here, which I call layers, U sub n and S sub n. And the key is that the U sub n, its image under F is U sub n plus 1, and the image of S sub n is S sub n minus 1. And of course, you can repeat this over and over k times. And so if you have a an intersection of U sub n and S sub n, then f to the k of x must be in U sub n plus k and S sub n minus k. And you would always choose k in such a manner that n plus k and n minus k are either equal or only differ by 1. And when you're looking for a trajectory, you may as well find any point on the trajectory, right? It doesn't matter. So essentially, if we want to find all the trajectories corresponding to heteroclinic connections, we just need to look at layer pairs of the form U sub n and S sub n, or U sub n and S sub n minus 1. So now that we have this, let's say we have, of course, a W of theta and S representing our manifold. Now we can always compute the exact values of the manifold on a finite grid of theta and S values. And then we just connect consecutive theta and S values together to form a rectangular mesh representation on the computer of our manifold, and then connect the diagonals as seen here. And so now we get a triangular mesh representation of our manifold in our 4D map phase space. So the problem of finding manifold intersections is the problem of intersecting triangular meshes. So now let's say we have, of course, we find the portions of the meshes corresponding to the different layers, and then we try to intersect the layer parts of those meshes corresponding to the layers that we identified earlier. And let's say we have, have identified the mesh points that correspond to given layers. And then we can connect, of course, define, as shown earlier, stable and unstable triangles and quadrilaterals, just indexed by I, K, J, and L. So the quads, I'm going to refer to them as QU and SU. And we basically want to see whether any QU intersects any QS in the full 4D space. And we define a quad as intersecting if any of the triangles on one quad intersects any of the triangles on the other quad. And this is just graphically representing the notation I use, where a QU is made up of a TU1 and a TU2, and similarly with each QS. So the thing is that these meshes often have tens of thousands of quadrilaterals in them, even for a given layer. We might discretize theta in like 1,000, 2,000 values. Then S might have like 35 values in a given layer. So if you naively were to check every quad on the unstable mesh with every quad on the stable one, you'd end up with billions of pairs to check, which if triangle-triangle intersection checks in 4D space, doing it billions of times is completely infeasible, computationally speaking. So what we do is we take some inspiration from collision detection algorithms of computer graphics. And basically, collision detections, okay, you've got a set A and set B. You want to see if any object in A collides with any object in B. And if you were to do this, every pair would be very expensive. But what you can do is you can quickly get rid of most pairs in what's called the broad phase, and then only apply your most precise tests that are most computationally expensive to what's left over, which is usually not much. And that's called the narrow phase. So that's what we do with our quad pairs, QU and QS. And so the first thing, it's called a spatial partition, uniform grid spatial partitioning. The concept is extremely simple. You just divide the kind of your world that contains the manifolds you're looking at, the layers, into series of cells or boxes, and you say, okay, two quads can only intersect if they belong to the same box. And the key here is that you don't have to deal with quad pairs. You can assign a quad to a box just by basic subtraction and division, and you only have to do that once for each quad, not for each quad pair. So that's order magnitude A plus magnitude B, not the product. Of course, graphical simpler representation. Here, if you were to check every pair of objects, you have 28 pairs to check. But if you see only the pair in box 1, 2, one pair in box 2, 3, and one pair in box 1, 3 can possibly intersect. So that you only have to check 3 pairs instead of 28. So then the second test, also very simple. You just see if the maximum x coordinate of one quadrilateral is less than the minimum x coordinate of the other, they cannot possibly intersect. Same with all the other y, x momentum and y momentum coordinates. And the basic graphical representation is that it's as though you make a box, a minimal bounding box around each quadrilateral, and see if those boxes overlap. So again, if the boxes don't overlap, they cannot intersect. It's all very simple, just less than greater than checks. Nothing, no normal forms, nothing complicated, right? And then the last part of the broad phase is that we just check, okay, you've got one quadrilateral made of two triangles. Take the equation of the plane of those two triangles and see if all the vertices of the other quadrilateral are on the same side of those two planes. If you have all vertices of a quadrilateral on the same side of the plane, well, that cannot possibly intersect that plane then, and that triangle. So by just doing that, we can get rid of a whole bunch of other quadrilateral pairs. And this is graphical representation of the situation again. And so now finally, usually this previous 3 steps of the broad phase get rid of something like 99% or even 99.9, or even sometimes 100% of the quad pairs. But for whatever's left over, that's just going to be a linear system to solve. So you take, of course, the 2 vectors spanning one triangle in the quad to 2 vectors spanning the other one. Solve this equation here for A, B, C, and D, and check if the solution belongs to the convex hull of both triangles. And if so, then we know that those triangles and, of course, those parts of the mesh intersect. And in fact, you even get an approximate solution to the original equation that's shown you for theta u, SU, theta sub s, and S sub s for the parameters of the parameterizations. So you can compute that intersection. And we implemented all of this using Julia, the Julia programming language, and OpenCL, which the key is that GPUs are really good at doing a huge number of tasks in parallel, as long as they're all exactly the same task, just on different data. So it's a single instruction, multiple data kind of programming model. And basically, we sent the second and third parts of our broad phase to the GPU. In the first part of our broad phase, which is just basic, like you don't have to do on pairs, we did on the CPU because you don't have, that's only on the order of tens of thousands of times, not billions. And then the last step for the linear system solver, that's too complicated to do on the GPU, so that was sent to the CPU as well. And finally, we benchmarked this actually just for consistency with some of our past studies. We benchmarked this using some consumer machines on manifolds from a planar elliptic restricted three-body problem. But keep in mind that after you have the manifold meshes, the rest of this algorithm is completely model independent. It doesn't depend at all on the equations of motion. So this is just a computational check here because in order to compare with the performance of some of our previous studies. And we saw some good performance. The bottom is if you turn the GPU off, and the top is if you turn the GPU on. And we see a good improvement. And some of you might have seen the previous version of this talk where I didn't include some of these steps earlier, and just wanted to mention that our results here, we got like 10 seconds on this benchmark. The last time you might have seen me talking about this, I think that number was around 30 or 40 seconds. So it's been improved since then as well, even using the GPU. Now, so finally, we want to use all this for actually looking for these resonance transitions. So let's say M1, M2, and M3 are Jupiter-Europa and Ganymede. And now, just a notation, M to N resonance means M spacecraft revolutions around Jupiter, and for the same time that the moon at the end makes N such revolutions. And so what we're really interested in is Europa. There's a lot of interest with Europa Clipper, the JUICE mission from ESA on exploration due to the subsurface ocean. And so, the thing is that usually when you enter the Jupiter sphere of influence on such a mission, you start out with a high sending major axis, and then you use engine burns and flybys of moons to decrease that. Again, related to stuff Professor Ross was talking about in the morning. And so previous studies by my mentor at JPL, Dr. Anderson, and Martin Lowe, shown that kind of the last few steps of this are a 3-4 to a 5-6 to the L2 Lyapunov periodic orbit in Jupiter-Europa if you're trying to land or start to get captured in the Europa region. So the question is, okay, before that, where should you come from? So which Jupiter-Ganymede resonance should you try to find a switching orbit from to that 3-4 Jupiter-Europa resonance? Okay, so for this, probably the most promising one we found is 4-3. So we computed some tori here up to unstable multiplier about 2.42. And we can see the family of tori we computed here. I'm just going to mention, quick aside, that for larger values of the unstable multiplier, we suspect that the tori may no longer exist. There might be something else there of a different topology, which we're still investigating, because as you can see, it's clear that the number of Fourier modes is starting to increase. We might be starting to get affected by a nearby resonance within the resonance, so to speak. But anyway, so at least for that most unstable Jupiter-Ganymede 4-3 resonance, we want to check if it manifolds approached or those of the Jupiter-Europa 3-4 with an unstable multiplier of about 0.11. So that was pretty unstable. So that's a stable multiplier, right? So we're a stable manifold. So here we just show a plot in Jupiter-centric Dylanic coordinates, L on the big L on the x-axis and big G on the y-axis, and we can see that this right there is the 4-3, and you can see also 3-4. represented in yellow, and then the manifold, the unstable manifold is in red, and the stable manifold that we're trying to intersect is in blue. So the actions are close enough together, and it seems that the actions do kind of come close together. But keep in mind, none of this has any averaging done to it. This is just in the full system, so of course the angles may not line up. And indeed, so far we haven't found a full intersection, but we globalized these manifolds out to layer 12, and we did find about 227 approximate intersections. Again, we're hoping in the future to find some actual intersections, perhaps of other family members, but this is what we have so far. And we did find some with reasonable delta V's of between 100 and 200 meters per second, about 12 of them with about 150 meters per second, and a lot more if you're willing to go up to about 200 meters per second between this 4.3 and the Jupiter-Europa, the Jupiter-Ganymede 4.3 and Jupiter-Europa 3.4. And just here we show a few such mesh intersections. You can see that our unstable mesh there, by this point, it's been globalized out enough that it's gotten pretty coarse, but yet we're still able to get those solutions with relatively small changes in velocity. And I have to mention that those velocity errors are not at all optimized yet. They're just whatever the mesh search gave us. So definitely, I think that if you were to shift around your position a little bit, you could get an improvement on that. And so one thing, though, is that these manifolds, we did have to globalize out about 9 layers on each side. So which refers to, you have to sum the layer indices. So that gives total flight time from the immediate vicinity of each resonant orbit to the immediate vicinity of the other of about 18 Ganymede revolutions, which is, I think, about 128 days. So if you want to shorten this, what we really need is some more unstable Jupiter-Ganymede 4.3 orbits, which, as I mentioned, probably we're suspecting that there's a resonance within the resonance. Basically, it's you have the Jupiter-Ganymede resonance, their periods being resonant with the perturbation from Europa. So we're probably going to have to do some investigations of orbits with different topology there. I definitely had some interesting discussions with folks yesterday about this problem. So, and we also, just to mention, did a similar study with Jupiter-Ganymede 7.5, and we found here the unstable multiplier was only about 1.4 because these come closer to Europa, and it's more than that perturbation gets stronger quicker. And so we globalized these to layer 15, but only found a few ones with a few approximate intersections with small errors in velocity. And the time of flight is also very large, so we don't think that 7.5 is going to be as useful here as the 4.3. We think that the 4.3 is probably where it's best to look more. And one thing is that we don't think that there are going to be too many orbits in the 7.5 Jupiter-Ganymede resonance with large unstable multiplier, just because the ones corresponding in the planar circuit problem, their orbits actually intersect that of Europa, so they would totally break down due to collision. So finally, in conclusion, we've kind of described this model, which we used for the restricted four-body problem, and then describe our GPU-assisted methodologies for finding these manifold intersections. It's, as I mentioned, once you have the meshes computed with numerical integration, it's entirely model independent. And so we showed some preliminary results, approximate manifold intersections. Hopefully in the future, we'll have some actual true heteroclitic connections as well. And we really think that the 4.3 is where we might see some connections with the Jupiter-Europa 3.4, which is the important gateway for final approach. And so, as mentioned, basically our future work that we have in mind is to try to find some of these more unstable Jupiter-Ganymede 4.3 resonant orbits, as well as their manifolds and hopefully connections. And then we might also, one thing with our manifold intersection program is we did everything there in Cartesian coordinates, x, y, x momentum, y momentum, but maybe if we can replace some of those coordinates with, say, Delaunay action L or Delaunay action G, we might see different or more effective results. So thanks for attending, and happy to take questions now.